Welcome back to week 6 of Introduction to Quantum Computing. We started way back in week 1 with an introduction to linear algebra. We talked about Dirac notation, qubits, multiple qubits, what you can't do with qubits. So we saw the no cloning theorem, the no deleting theorem, and we saw Holevo's theorem, which said that a qubit can only convey one bit of information, and n qubits can convey n bits of information. This may have sounded a little bit strange because the qubits were specified in terms of complex numbers which have the same cardinality as real numbers, so it seems like there's an uncountable amount of information in them, although the measurement which collapses this state into one of two possibilities shows us that, in fact, there's only two possibilities, so only a bit of information can be retrieved from the qubit. Now we're going to look at our first quantum protocol, which shows, in fact, you can convey 2 bits of information with a single qubit, so long as you have some entanglement beforehand. So this kind of communication protocol usually has a couple characters, and they're given names, typically Alice and Bob. And Alice and Bob can agree on a strategy beforehand. Alice might say, I'm going to do this, and when I do this, then you're going to do that, and vice versa. And they're typically constrained, so these protocols ask them to achieve some goal, which you can think of as some game in which there's some win condition and there's a set of rules that they have to obey. Now the rules change from game to game, so the most general game would be one where Alice and Bob can send back and forth bits of information, or they can send back and forth qubits of information. So in this particular game, we're going to assume that Alice can only send a single qubit to Bob. Bob can't send anything back to Alice. Alice cannot send any bits to Bob. All she can send is that single qubit. And she has to convey 2 bits of information. So Alice and Bob require some strategy beforehand. They can share an entangled pair of qubits, and this you can already see is somewhat necessary because in order for Bob to get 2 bits of information, he needs 2 qubits at some point. So Alice is going to send him 1, that means he needs to have 1 with him, and Alice's qubit can't have on its own conveyed a single 2 bits of information. It must have been the 2 qubits combined, so it must have been an entangled state. So Alice and Bob, they will share entanglement beforehand, and then we'll derive a strategy for them to use to code and then decode these 2 bits of information. So we already know how to create entanglement, so let's draw a circuit. This will be Alice's qubit, Bob's qubit will be down here, and Alice will apply Hadamard and then a C0. So these qubits, if they're represented by physical things, have to be like in the vicinity of each other. And afterward, let's ignore the normalizations. We end up with this 0, 0 plus 1, 1 state, which we showed was entangled. So there's still a cut here. So there's 2 qubits. And if we imagine that these are represented by physical systems, Alice can retain that physical system that's representing her qubit, Bob can retain his, and then they can kind of separate. Alice can then decide at some point in time the 2 bits of information she wants to send, encode that into her qubit, send the qubit off to Bob. Bob decodes it and finds out what the 2 bits of information were. So what does Alice's strategy look like? So she's going to perform some unitary. That'll depend on the 2 bits of information that she wants to send. Let's call them B1 and B2. And then Bob's going to do nothing. and Alice will send her qubit to Bob. Now this action is applied to this state, but we see because of the tensor product structure that this just looks like, it's ignoring the bits for a moment, U acting on the 0 state, tensor the 0 state, U acting on the 1 state, tensor the 1 state. Now, we saw that these product operators, one which are just a single tensor product with no sum, can't generate entanglement when starting from a product state. Now, these operators may not be their own inverse, but their inverse has the same form. So if I take the complex conjugate transpose of this to obtain the inverse, I still have this product operator. So that means that the opposite is true, that we can't go from an entangled state to a product state with a product operator. So this state is still entangled, and we're not going to get a deterministic outcome for Bob when he performs the measurement. So what Bob needs to do is obtain a state that looks like something like this, whether the location of the B1 and B2 don't matter, but without loss of generality, it looks like this, so that when he measures, he gets one of the 4 outcomes, 0, 0, 0, 1, 1, 0, 1, 1, and these are one of these is the 4 bits, or the 2 bits of information that Alice wanted to send. So what can we do? Let's work backward from this state. We know that this state going backward in time has to become entangled, right? So it was this entangled state here. It's this entangled state here. Alice has done something to it. It has to be disentangled, which means we have to perform some sort of joint operation. We created entanglement with this operation, so let's try to do that in reverse. So working backward, Bob has to have this state here, and that, working backward in time, was an entangled state in the past that depended on what Alice actually did to her qubit and sent to Bob. So this top qubit here came from Alice somewhere, and the bottom qubit was the one that Bob always had. So Bob is going to disentangle these 2 qubits and end up with this product state. So these operators happen to be their own inverse, so we don't need to take any complex conjugate transposes here. So let's just work backward from this state. So we have B1, B2, and then identity tensor H, and then a C0. Okay? So let's apply the H, the Hadamard tensor identity first. So we have the C0, it's still there. And then the Hadamard is applied to the B1, and B2 is just left alone. Now, it's helpful to have some identities hanging around that tell us how these special operators act on an arbitrary qubit. So if I have a Hadamard and it acts on 0, it goes to 0 plus 1. If it acts on 1, it goes to 0 minus 1. So that means I can write it as 0 plus minus 1 to the power of that bit value, 1. Okay, and you can double check. If B is 0, I get 0 plus 1. If B is 1, I get 0 minus 1. And remember, pretty much throughout this calculation, we'll ignore any of these normalizations, so we don't have to be writing square roots of 2 everywhere. So let's just apply that formula. So we have C0, and then we have a 0 and a B2. plus minus 1 to the power of b1, 1, b2. And now we can apply the C naught quite easily. So the C naught is the operator that works as if the first qubit is 0, then the second qubit stays the same. If the first qubit is 1, then the second qubit flips. So in that first state, the first qubit is 0, so nothing changes there. And we have some constant, so that stays where it is. And now we need to flip the bit of the second qubit, right? So if that B2 was 0, then the 1 would flip it to 1. If the B2 was 1, then the 1 in the first qubit would flip it back to 0. So the overline there is the not operation. So it's the opposite of the bit. Okay, so this is the state that Alice needs to create. She needs to apply some sort of operator to encode these B1 and B2 in this way, starting from the 0, 0 plus 1, 1 state. So 0, 0 plus 1, 1 has to end up as the state above. All right, so we have a minus 1 to the power of B1 in front of the 1. What kind of operator does that? Remember that the Z operator is exactly this kind of operator. So Z takes 0 to 0 and 1 to minus 1. So if we write it like this, Z acting on B, any bit, let's do it off to the side as we did for the Hadamard. Z acting on B is minus 1 to the B, right? So if the ket is 0, then it stays as 0. If it's 1, then it goes to minus 1. And we see already up here that that's exactly what this thing looks like. So we have a Z to the B1. That's obviously acting on Alice's side, and we'll recover the state if we perform that operation. Okay, now it seems like there's a problem because Alice is the first entry. This is Alice. Remember that we have a tensor product here implied. So every first entry is Alice, and every second entry is Bob. How is Alice going to encode something on Bob's qubit? She doesn't have Bob's qubit, she has her qubit. Well, just as a quick aside, we can note the following. If I have the entangled state that I'm looking for, our favorite entangled state, and I apply X on the first qubit of this state, then what I end up with is flipping that first qubit 1, 0 plus 0, 1. And actually this is the same as if I applied X on the second qubit. 0, 0 plus 1, 1. And I'm going to flip the second bit now, so I have 0, 1 plus 1, 0. But although things don't generally commute in quantum mechanics, here I'm just adding two vectors together, and it doesn't matter the order in which I add vectors together. So in fact, these two things are the same. So if I apply an X on the second qubit, which it looks like is something that I'm going to want to do in this original equation up here, that's the same actually as if I applied X to the first qubit. So we can verify for ourselves that this equation can be rearranged. So the state here can be rearranged so that that bit value is actually on Alice's qubit. And that's really kind of the beauty of entanglement. So let's just check if B2, the second bit, is 0, then in the upper equation I have 0, 0 plus 1, 1. In the lower equation I have 0, 0 plus 1, 1. If B2 is 1, I have 0, 1 plus 1, 0. In the upper equation I have 1, 0 plus 0, 1 in the lower equation, and the order in which we add those two vectors doesn't matter. So in fact, these two things are the same. And then we can immediately see that to obtain this state from 0, 0 plus 1, 1 is to apply an X operator if the bit value is 1, and do nothing if the bit value is 0, as we see in this aside equation here. So we have the Z acting after the X. Nothing's happening on Bob's side as required, and we end up with the desired state is equal to the original state that Alice and Bob share after applying an X or a Z, depending on whether or not Alice wants to send a 0 or 1 bit. Right, so there's 4 possibilities. So either Alice does nothing, which is what she'll do if the bits are both 0. So Z to the power of 0 is identity, X to the power of 0 is identity. Let's write these down. So we have B1, B2, and then let's say this is what Alice does. 0, 0, 0, 1, 1, 0, 1, 1. Alice will apply the, so she's going to apply the identity, in this case, Z to the 0, X to the 0. In the next case, she applies X because Z, we have B1 is equal to 0, so Z to the 0 is identity, X to the 1 is X. In the next case, we have just Z because B2 is 0. And finally, we have ZX. Okay, so she's going to do one of 4 kind of very distinct things. So initially, maybe you thought, oh, she's going to apply some unitary up here, maybe with trigonometric functions and some continuity, but Bob at the end of the day needs to have a definitive outcome, so he really needs to have these things kind of separated. So that's kind of the intuition for why Alice is going to perform some quite distinct operations. So she does have a unitary. It does depend on B1 and B2, but it doesn't vary in some smooth way. Okay, so we have these kind of quite nice distinct operations that she's going to perform. The whole protocol then looks like as follows. So Alice and Bob, they have these qubits. They're together and they create some entanglement. Then Alice, she takes off with her qubit. Bob stays where he is. And then at some point, Alice decides, here are the 2 bits that I want to send to Bob. First she applies B2, right? B2 is applied first, and then B1. So these can be conditioned on some classical values, B1 and B2. So she changes her qubit, or possibly applies the identity. Bob doesn't know what she's done. She sends her qubit back to Bob. Bob disentangles them. And then he performs a measurement, and the result of the measurement is deterministic and is B1 and B2. So we can verify that this all works out nicely using this quirk simulator that we've seen in the previous lectures. So we have our quirk simulator here, and we have the circuit. Let's move down. So we want to create this circuit that's shown on the bottom. We'll create this entanglement first, giving ourselves some room. So this will create an entangled state as expected. So we'll have superposition between the 0, 0 and 1, 1 on the bottom 2 qubits. That can of course be undone. And in between these two operations, we need to allow Alice to encode the bits that she wants to send. So first there was an X, and then there was a Z, and these are conditioned on these 2 bits that Alice wants to send. So within Quirk, we can flip the qubit value. So here we have 0, 0, and Bob down here at the end of the day measures 0, 0, so we can put some measurements on there. If we flip one of the bits, we see that Bob's bit also flips as expected. So when Alice wants to send 1, 0, Bob measures 1, 0. If she wants to send 0, 1, Bob measures 0, 1. And 1, 1, Bob measures 1, 1. And we can watch this happen by playing a little trick here. So we can cycle through all of the possible values by using this counting gate that's available in Quirk. And you can see, remember in the protocol there was actually Alice performed some measurement, so we can see those measurement values and how they match up. When Alice measures 1 or 0 randomly, that information gets sent to Bob through this qubit that Alice has. Okay, so Alice has the this qubit on the 3rd line. She takes that off to her own laboratory and encodes the X or the Z depending on what bits she wants to send. And this up here is just kind of simulating Alice's choosing bits at random. And we see that they match up on Alice and Bob's side. All right, so that's the Superdense coding protocol. Next, we're going to see the opposite of this protocol. But before we finish, you might be wondering, well, why on earth did we do this? Certainly, if Alice wanted to send 2 bits, she could have just called Bob on the phone or send him a message through text or instant messenger to communicate these 2 bits. However, if she did that, then that could potentially be heard or transmitted publicly or not encrypted. When she sends the single qubit, an eavesdropper can intercept that qubit, but can only ever extract a single bit of information as per Holevo's theorem. So if an eavesdropper obtains a qubit, she can only get 1 bit of information from it, but Alice actually encoded 2 bits of information because of this shared entanglement initially with Bob. So the eavesdropper does not have shared entanglement with Bob, so she or he can't figure out the 2 bits that Alice sent. So this Superdense coding protocol actually has applications in quantum communication and quantum cryptography. And that's possibly something that we'll see later on in the subject, or one or a subset of you will do in one of your projects.